friends, I want to welcome you. We're not many, but at least some of you want to hear us. I want to introduce our speakers, Anton Guglya, the CEO of QApp, Pavel Vorobyev, the Executive Director of the QRate, and
Korostelev Pavel, руководитель отдела
Korostelev Pavel. He is promoting products in Security Code Company. Well, that's not in a lot of us, but I believe we'll have a very intimate discussion about should we be afraid of the quantum tech and everything thereof.
We'll talk about quantum technologies, and it seems they are, but maybe they're not. And we know they exist, and we know from quantum physics of quantum space, and they don't exist because we don't see them. So
that's why, for a number of reasons,
it turns out that for many years we've been building quantum computers. Is it a myth or reality?
We're going to
maybe it is a reality.
And how it is going to become a part of our lives and what to expect. And we are apprehensive of any technology because we use it for good, we use it for bad. And this happens like with any notion in life. So we gotta understand, is it applicable? Is it dangerous? And how can we protect ourselves from it? So my first question will be for Anton. You know, this is the way we do it. Anton, is quantum computing about the future or about the present? Both the future and the present. Dear colleagues, let's try to understand. If it's your first time about quantum technology, lift up your hand. Okay, sounds good. It looks like many of you have heard about quantum. Well, quantum tech is developing by leaps and bounds, not only in Russia, but elsewhere, but also quantum, calculations. And quantum computers are part of the quantum sensoric metrology calculations. Speaking of quantum computers, why are they real? Because they do exist. There are like companies like IBM and others, they have like very, very strong quantum systems. Yes, they do not solve like industrial kind of scale tasks. How about Russia? I wanted to say that in Russia, we also have quantum computers. Lift up your hand. Do you know that the first version, iteration of quantum computers know it? 10% of the audience. Well, we have identified you guys. Yes, in Russia we have the first quantum computers that they've been launched, not even in this year, but before. It's a Rosatom state corporation, and it's pursuing the roadmap of quantum calculations. It's quite a big program with a KPI in engineering that is to build quantum computers of different architecture to boost up their capability and give it in the hands of business, but also do the first experiments. They have been done, and there are thousands of experiments which have been done on the Russian-made quantum computers. 20 qubits and less qubits. They're all within the perimeter of the Rosatom Corporation. They're being developed by the big consortia of the schools, high-tech companies. And speaking about the potential threat, we are not expecting of those computers which are being developed in Russia. Not only because their capacity is not too high, well, it is less than the international computers, but they're being developed to work on the very complex tasks, not crypto, but modeling physical and chemical systems, optimization, logistics. But speaking about international computers, which are much more powerful, and they have developed like further than the Russian ones, we're beginning to think, cryptographic community, information security. We are thinking that those quantum computers could be a threat. Yeah, we can develop that. Yes, we're going to get back to that. Pavel, do you believe in that? And tell us, please. You are from the company. I'm going to say that you guys you've done some real exercises, some real cases, but your belief in the quantum computers, do you believe in it or not? Since I'm a systemic technician in my education, I really like computer science and I really like all things quantum because it's a different logic in what we have in our conventional equipment. It's everything. Everything is different from the basic elements, and it is not like a Euclid's geometry. They decided to make a different geometry, but they've just revealed a lot of things, and uh, and quantum calculations are helping us to do certain optimization tasks and finding different nonlinear things. It's inspirational, it is great, but also it's quite specific for the information security, specific applications, which we are going to catch up with in the next 10 years. Yeah, we're going to come back to that. Pavel, how about real life? Yes, in real life, we expect its application uses in biology, in optimization, in all those things where you cannot do it with a conventional tech. I also wanted to add about industrial use. We have a lot of quantum calculation cases, maybe like hundreds in the open domain. Most of those quantum cases, it is about using digital twins of quantum computers. Maybe definition is not right, but I'm speaking about emulators of quantum computers. Basically, those are software packages which on calculation level they use CPU, GPU clusters, but to a certain extent they emulate quantum computer. And those emulators, they're also progressing as fast as hardware, but they are easy to pilot. So basically, it's a software. Yeah, absolutely, 100% software. Yeah, sometimes you have like a hardware accelerated emulator, but mostly it's a software which is piloting a quantum algorithm for optimization, genetics, biology, financial optimization, lots of cases like that. And business is expecting that those algorithms, which they will test and emulate, they'll be able to put it on the quantum computers. This is how it works in Russia and elsewhere. Simulators, that is. I got it. Okay. Thank you. I think me and my team, we do believe that quantum computers, they will be developing, evolving very rapidly. At the same time, I want to add to what Anton has said. I believe, and I think that our quantum computers will also be used for cyber attacks and for hacking the code, for breaching the code. Let's be honest here, okay? Let's be honest. If they do it on this side, on that side, they'll be doing it only from this side too. And what I want to say is, we know that yes, officially there are like 1,000 qubit, 20 outside. But how many qubits in China? No one knows. If we'll take 50 computers, 20 qubits each, we're going to catch up. Not exactly like that. It doesn't work like that, but frankly, we are not going to find out when a quantum computer will be created, which will be worth of be used for cyber attacks. Here's my favorite example. Let's go back to the World War II and Enigma machine. You remember? No, let's not scare people. No, let's not. Let's talk about peaceful things. Yeah, but the Enigma machine was code break in 1942, and the Germans learned about that at the end of the war. But now, what I'm trying to say, how can we use it in a peaceful life? We do believe, and I'm also a believer, and I guess many of you guys do. And okay, that's fine. So, if we got it right, the quantum tech and quantum computers we're speaking about, they are being used they are being used to process lots of data which a regular computer, no humans will not be able to manage, will not be able to process. And quantum computer is only able to process this much data. Yeah, I think this will be the case in the future, but today it is not so. And today It's a technology which is in the beginning stage of its development, and this, beginning phase is like taking decades. Okay, what's the goal? What's the goal? Well, the goal is in the future, absolutely. Those goals which a regular classic computer cannot do for optimal time, the quantum ones will be doing it much, much faster. But it's not all the goals because quantum computers, we believe, and I think the part of the community also does believe, that they will never fully replace the classic ones. They'll be complementary depending on the class of tasks. Yeah, quantum computers are not going to wash lots of dishes. You need hands. But again, I guess the main message is like it's gonna be like huge calculations. We cannot do them with existing hardware. Okay, fine. And then, as it was mentioned by Pavel, any computer may be used due to its capabilities in different assignments, for different purposes. And now my main question is, should we be afraid of those, potential threats? If yes, no, should we start sweating right now out of fear, or we still have time to live in a peaceful life, kind of, because Pavel has mentioned about that. My opinion, we have to start worrying right now for two reasons. We will never learn when the strong quantum computer is going to show up, which will be used to the detriment for the bad purposes. And according to different perceptions, the strongest quantum computer will be used within 10 to 30 years. And now we have data. We have data which its lifetime is surpassing its horizon. What Anton has mentioned, these are the kind of attacks when keep it now and break it later kind of attacks. Yeah, this is actually the case because one of the modules of quantum threats is a quantum threats, and oftentimes when people say quantum threats, they imply hard now, or still now, crypt later. Any attackers, they may steal data today, but they're being crypto ciphered by traditional algorithms. But then when they get access to the strong quantum computers, they'll be able to crack the code and get access to the data. And if the value of the data will be equal or more, then when they will get this access, this has to be protected. It has to be protected today because we all know that there is some data with a life cycle of decades. It's valuable for business and even for individuals. So we may assume that now somebody's stealing this data, storing this data until they will be able to get access to such a computer. Pavel, what do you think? I would like to highlight a couple of things. Yes, the hackers, when they are in the victim's infrastructure, they're looking for encrypted data and kind of leaking this encrypted data, or having it connected to the they just dump internet traffic to be able to do something. Well, actually, it is not such a strange attack because even without using quantum technologies, just by analyzing metadata, you can learn a lot of things. And there are some people who developed this technology. They got some medals on both sides of the equation. There are also a bunch of attacks, the bad ones. Those are attacks related to collisions, like e-signature, for example. Electronic signature is the main mechanism to ensure the authentication, authorization, etc. And your goal is number one. And for example, when you do the like a closed circuit in software, so any attacker having a quantum computer, they can build an attack, they can implement attack for collision, and to make their own file, sign with a known key their file, and this file will be able to go through the all mechanisms of detection and prevention, threat prevention, simply because e-signature is valid, it's all good. Second is authentication. And since for about 15 years, corporate perimeter is being diluted, and now what's important for the corporate user is how they can authenticate themselves. And the more quantum computing is growing, the more we have the problem related to authorization attacks. And again, it's VPN and communication channels are vulnerable because on one hand you have asymmetric cryptography and non-symmetric cryptography. For asymmetric you have a Shor algorithm. For symmetric you have Grover algorithm, and now we have a trick because all of our protection tools which create a communication channel, they it's a 256 bit, the encryption key, and to be able to get the good protection from the quantum attacks for the brute force, you have to double or triple the key. And in the same number of times, your throughput capacity is going to drop. Or you have to buy stronger equipment to be able to deal with it, or you have to suffer because the throughput capacity of your channel is going to be dropping. But since throughout the whole time of developing computers, we've never had a situation when the amount of megabit and gigahertz would drop, it's going to create quite a big workload and stress on the infrastructure and those apps which will be working in the future. And we have yet another problem, that if this will be some kind of alienable, like firewalls and something like that, crypto gates, they're limited on the hardware, but we'll work with them. What shall we do with the cryptography which is built into the apps? You know what to do, because right now we've known for a long time. That would be great to learn how to work with the cryptography. You don't have to have a hard code. Separate people have to audit application with the cryptography. And this is why when you're building in certified cryptography, some people are going to check and make sure that you're working with the keys, because it's important. Anyway, still, we do have a very low culture of cryptography management. And when we'll have the implementable attacks on cryptography with the quantum computers, we'll say, oops, it's really bad. And now it's not about even the tech, but about methodology. To respond to this problem, we have like a crypto agility concept. This is when you have when you know that probably these encryption algorithms probably will not be enough at some point. You do not know which algorithms you may need to implement, and lest this happen in your application, you make a provision for replacing algorithms with new algorithms. And this is one key thing which we have to engage in right now. Yes, we do not know what will be post-quantum cryptographic algorithms and which will be applied. Yes, we do not know when we'll have the efficient quantum computers for implementing cryptographic attacks. But today we have to start thinking about how to replace this cryptography on a more sustainable. Very interesting. But I have yet another question. I've been hearing a lot that next to quantum technologies and quantum cryptography, we have like a post-quantum cryptology. Anton, can you please clarify what does it mean so that our audience, they would know what's the difference between the two? It's like a rumor that post-quantum, it's even cooler than quantum, because there is a quantum threat and a post-quantum defense. Is the hype? Is it real? I guess we have to look into etymology, because post-quantum cryptography, we're mostly speaking about asymmetric encryption and more about the software solutions of the new algorithms. And quantum physicists, there's no quantum physics in the post-quantum cryptography, unlike quantum cryptography, where there like a quantum physics principle to be able to pass on key information. And this cryptographic key would be transmitted with the quantum effects. So post-quantum cryptography is basically a new encryption algorithm. It's asymmetry and digital signature, and this would also be a software solutions built on those algorithms. Quantum cryptography is a cryptography built on principles and the laws of quantum physics, and it's more about distribution of a cryptographic key. I would say these are the main differences. And both of those technologies, they do not contradict. They may be used synergetically.
Post-quantum algorithms, they're used for quantum communication when they communicate between the vendor networks or identification of new devices, or they can use separately. And how to use it and what technology should be used, whether it should be post-quantum or quantum technology, you need to look first at the level of how they work with the data and the level of infrastructure to which cryptography should be used. For example, post-quantum algorithms should be used for client-server communication, for uh, protecting yod gates and many others. At the same time, quantum communications properly to use to distribute keys from data centers. And so say both technologies are developing in parallel, both in Russia and in other countries. They are regulated in a certain way. They have vendors, they have system integrators that test technologies, and they develop all together. If I understood you correctly, let me sum it up. Post-quantum, this part of the word post, it doesn't mean that after. It's kind of above, right? Above quantum. No, it's both. Post in cryptographic community, they say that post-quantum cryptography, this is cryptography that will be valid both today and at the point when there will be very powerful quantum computers, but the data will be properly protected with these new algorithms. You can look at it both ways. So it doesn't deny the fact that technology exists. And I think that this technology will replace this current cryptography. Post-quantum cryptography is about revolution in cryptography, but also about evolution of cryptography. So asymmetric algorithms, they will replace new asymmetric algorithms. There will be new standards certified, and they will begin using them as we use conventional solutions today. Okay, it's a little bit clear now. We'll discuss more. So now we know that there are quantum computers. There is a possible quantum threat. It's kind of scary to say the word. And say this is something that is way more powerful than the conventional systems. Oh, yeah, you're right. Okay, understood. But the same capabilities, the same technologies can be used for protection, right? Because conventional systems won't be able to deal with that and won't be able to protect. So we need kind of the same capabilities to protect ourselves, right? So Pavel, so in this part, what we may count on, should we hope that we can use it for protection, not for attacking, protection from attacks? So what possibilities could be? So if we're talking about quantums in general, so there are, as Anton said, there are quantum cryptography, right? So we can start with this. Today, in the world and in Russia, there is quantum cryptography, and Anton said that first of all, we're talking about quantum distribution of keys. When between two accounts, they use fiber optics. So it's a user account encryption. No, it's not encryption. It's a key distribution. Then cryptographic keys are used by our partners like code of protection as classical encryption. Quantum cryptography is not even cryptography. It's about distribution of keys, cryptographic keys. And they use quantum physics principles in them. So, and it actually exists in some solutions. Not only they are actively applying it in the world, in Russia today, by the end of the year, They'll build about 7,000 quantum networks. They have quantum communication roadmap, and Russian Railways actually monitors the situation. So Moscow, St. Petersburg, Moscow, Nizhny Novgorod, Moscow, Sochi, all the Volga region. So they need data centers. Yes, there are some trusted hubs that they use for that. So all depends on the quality of fiber optics. Everybody works with the losses of 20 decibels. It's ideal fiber optics up to 120 kilometers. So if it's a city, this is 30-50 kilometers. If it's a data center to data center, it's probably 58 or something like that. Okay, another question. Is it true that they published in newspaper about the satellite channel with quantum distribution with China? Yes, right. Have you heard that? Have you read about it? Yes, right. So there is somebody who actually did that. Last year, QRate company, together with QSpace, they managed to demonstrate the third in the world and the first in Russia, the quantum distribution of keys using a satellite between Moscow, but say not Moscow, it was Zvenigorod, and Beijing. They used Chinese satellite. Sadly, now there is only one satellite. It's Chinese satellite that can distribute the keys. So we made agreements with our Chinese partners, and together we managed to distribute the key, and we exchanged encrypted messages. We sent them a quote. They sent us a formula. So we had a communication session, and it is quite an achievement because besides China and Austria were the third country that were able to demonstrate it. How livable this is, or it's very difficult to use. As of today, I think it's a prototype. Last year, they launched the first Russian satellite that will test the technology. It doesn't have the quantum part. They're setting it up for monitored on the ground, but I think the next 2-3 years will launch the first full-scale satellite with the quantum keys on board. So we don't have to worry about it because we actually can protect ourselves on a certain level, right? Anton, do you have anything to add to what was said in terms of protecting organizations using quantum technologies? What else could be offered? At least something that exists today. And are there any prospects in terms of evolution of this? I can tell you more about post-quantum algorithms. In Russia, there are many cases, and they're completed. They're done mostly in the financial sector. They're increasing the level of security of information exchange when bank exchanges information with their corporate clients, when post-quantum algorithms the pilot contours, they're integrated there, and they ensure a higher level of security. There are projects with NSPK, Russian payment system, and they also use it for the electronic paperwork exchange. There's quantum resilient blockchains and VKM systems and document management systems, communication services, messengers, if it's a corporate messenger that can be integrated. It is very actively developing. And besides those industrial cases, what's important, regulations that are used to regulate this. So regulations are on different level right now. So our national algorithms, post-quantum algorithms, there will be potentially new state standards. There are two algorithms that with high probability will be included in new state standards. So you can see them in repositories, and we can together develop them. And there are first projects of state standards of technical committee of a Russian standard, the consortium of industrial companies and scientific companies. They together developing these algorithms. And this is how bring together new regulations and to meet the needs of business and using quantum technologies and new mathematics. That's great. Pavel, could you tell us how different is the load on the infrastructure when we introduce quantum technology algorithms? So what should be changed? What challenges await those who are going to implement quantum technologies? If we're talking about quantum cryptography and quantum key distribution, so we have certain recursing. To have a trusted channel, you have to have a trusted channel. So you have to have fiber optics that you can distribute the keys clearly. We do a lot of research on transmitting photons through information channels through the satellite. Many studies are done. Some of them are classified, and we can't talk about them. But right now, if you're talking about realization and what Russian railways do, is a specialized channels from 30 to 100 kilometers. Between them, you put trusted hubs, and they retransmit the signal. And there are data centers, and you need to use fiber optics between them to use the distribution of keys. If they're in different cities, then it's a different story. From the point of view of traditional security of companies, so it doesn't impact a lot, but this additional infrastructure task, it will be important. Despite the fact what Anton said, it post-quantum algorithms, they're used for client service where we don't need the infrastructure, but where we need to work with an infrastructure, we need to think about dedicated channels. If we're talking about post-quantum cryptography, then it's one round of key exchange. The keys are pretty thick, so to speak. So it requires additional computing and resources for this computation. We need to assume those resources in the new infrastructure we're going to build. About the infrastructure again, post-quantum algorithms. So when they're employed, and they're especially those candidates to be included in the Russian standards, part of the parameters should be accelerated. And now we have first prototypes, crypto processors, and they can increase some of the parameters. And there are two approaches. One of them is on the processor teams. You accelerate the parameters. So in new version of processors, this should be included. So with conventional processors, that's the second one. Then you have crypto processors, and they accelerate this. So both things are happening in Russia, and they develop in kind of scientific part of the issue. So that's an answer to the question how to improve the work of post-quantum algorithms. So what cryptic co-processors? There's additional computing capacity that can be like a hardware. Yes, it can be a kind of separate component, and they use it to accelerate parameters. It's going to be one of the answers. It doesn't mean that everybody will have it tomorrow, but I would like to add here. Quantum cryptography in open space and in fiber optics, it doesn't replace one another. They work together. When we worked through satellite in 2019, when for the first time on the building of the Moscow Technology Institute, we tried to get the quantum key from satellite September, October, November. So how many cloudless nights we had? It's hard to say. 2. Well, at least it was in St. Petersburg. So it's so in other words, as I understand, so it's very meteorologically dependent technology. So it's not that cool. No, it's a cool technology, but it depends on the weather. So that's why where you have fiber optics, it's better to use quantum cryptography in fiber optics. And the speed in Russia is about 200 megabit a second to generate a key. So then there's another question. I think the Japanese started this. So now they build data centers in Siberia to cool them off using mountain rivers. But it's not really sunny days there. And when we have data center here and there, so you can do that using a radio channel. So if there is a data center in Siberia, they set it up with fiber optics. It's better if it stands on Trans-Siberian line. So, but if so, when you have a satellite channel, the quantum technology won't work, right? So, well, first of all, in Siberia, it's pretty sunny actually. Secondly, not everywhere. Then again, the key is accumulated, and the satellite flies from one point to another twice in 24 hours. So there is a guarantee that at some point the key will be delivered. So the question how fast depends on the weather, right? And secondly, if you need to put additional fiber optics for but now they do like in fiber optics, so you can transmit both information flow and quantum signals. So I think soon we won't be using dark fiber optics and we'll use conventional one. Maybe those who watch us online and in the audience, that's what I'm going to ask. So we have these great products with quantum technology. Say we have infrastructure company, and I would like to introduce a solution with quantum technology. So what I need to change in the infrastructure I have to use the technology? Well, it depends on what quantum technologies you'd like to implement. So if you're talking about quantum communication, then you need to introduce the solutions that have the optic scheme, Alice and Bob, as hardware modules, and then they put those modules in the encryptors. So I need to put something on the perimeter, right? In quantum communication, yes. So I put a hardware, right? Yes, you bring a new hardware in the infrastructure when you implement post-quantum algorithms that you don't have to change the infrastructure. But if you need to do quantum computing, so if you're talking about emulators, as I said, we talked about the software modules. So yes, modification of the infrastructure is not needed. So you can use emulators on the clusters you already have. They can be done on the cloud or in service provider, whoever say. So if your IP lets you do that, so then you'll be able to call them from there. But if you're talking about quantum computers, so far it's not possible. There are not such quantum computers in Russia that you can put on your perimeter. Okay, we're just simple people, and we're interested in technology and what we need to expect from technology in the future. Say it's both presence and future, but it's not so present that we can get the computer from the cabinet. But in order to get on that paths. We don't really need much, right? So we need to add some hardware to the infrastructure. So and for post-quantum, so we just need to use emulators and the whole thing will be working. But do you people have any tricky question? Something you're concerned with? Okay, so I have some concerns. Where? Okay, there's a question. Could you please, so please shout your question and we'll hear you. Quantum entanglement. It's very difficult to hear what the person is saying without a microphone. Could you just say a few words about quantum entanglement? There is a number of quantum laws based on which the technology is built, and also quantum computing. Quantum entanglement is part of it. Quantum technology is the possibility to use single quantums as ions, photons, and atoms to do some transactions with them and then build some computing on this cryptographic keys distribution. So they use a single state of photons, and on their polarization they encrypt the key. So quantum entanglement, this is one of such phenomena that allows us to do that. Quantum particles, they're entangled. So if we change the state of one quantum, the state of the other one will be changed too. So based on this law, many paradigms are built on in quantum computing. So quantum entanglement, it's one of the foundations that different architectures are built on. And there are many such quantum architectures, about 5, 6 that are priority that are developed in the world, and there's some additional ones. This is the superconductivity ones and many others. And so one of the quantum laws that you mentioned, yes, it's a foundation of it. So if you want to do that, so study that, and it is applicable in quantum technology. Yes, please. Could you tell us? There is bit 1, 0, off, on. What is qubit? What is qubit? So 1 hour wouldn't be enough to explain that. Yes, right. Quantum computers, they use such a state is qubit. It's quantum bit. It's the term that we use in infrastructure. And I'm sure that you've heard this. And in qubits, they measure the performance of quantum computers. But in fact, there are other measurements that you can be used. In qubit, this is the space state between 0 and 1. And this is something that differentiates conventional computers from quantum computers. If we use an example as a coin, then classical bit, this is the state of the coin. It's heads or tails. And it's just a hypothesis. It's not how they teach quantum physics in qubit. This is the coin in the air, and while the coin is flipping in the air, so the computer is trying to figure out how the coin is going to land, with heads or tails. Qubit is a different way of coding information. So in qubit shows the different states of particles, ions, photons, and atoms. From the point of computing, so you have register 8 bits. What is the maximum states you can encrypt with this? So it's alibi. So you think, okay, 2 in the power of 8. But the 8 qubits it's much more. Quantum register has more capacity than a conventional one. So what is bit and qubit? Bit is 0, 1, and bigger the qubit, it's the, say, capacity of registry is growing much bigger. So if you use qubits, qubit is much cooler than bit, 4 folds is minimum. Quantum key distribution. Oh, it's very hard to hear what the person on the floor is saying without a microphone. Sorry, I can't hear the question. On the ground, you have a telescope. We use 40 centimeters telescopes. On the satellite, there is a emitter. First, they synchronize them, and telescope follows the state of the satellite. So we set up a quantum channel, and it's like in sci-fi movies. Satellite sends single photons down to Earth. That's a flow of single photons. Clearly, most of them are lost. Even in an optical channel, very little of them get to the destination, but the speed of generation of those photons allows to generate information. So not every photon gets to the destination. Quantum and quantum technologies cannot protect, as far as I know. And they need protocols for that. Translator speaking, it's very difficult to understand what the person from the floor is saying without the microphone. I'm very sorry. I barely hear what he's saying. Are you talking about quantum technologies? No, it's right, and very interesting questions. Yes, right. First of all, we need to say that quantum communication has to do with crypto protection, and they should be properly certified. And yes, our regulator, before issuing the system and giving its certificate, they need to look at many attacks, Trojan horse and blinding of one photon detectors. So there is a protection for that. For example, QRate company, they use not a BB84. It is used with the costate. So there are many attacks like that, and it's all controlled by the regulator. So if you're curious, on Gazprom Bank booth, there are my colleagues, and they'll be happy to answer your questions. This is the booth that is outside with a small arena. About the attacks on quantum communications, I think in 2012 there was a Nobel Prize in physics that describes an attack on photon. So we kind of identify spin on a photon. Who got the Nobel Prize? I don't remember. Okay, dear friends, sadly the time is limited. I hope you got a little bit clearer idea that there are quantum computers, so they can be both useful and harmful. But if they're going to be harmful, we have something to respond to it. So we shouldn't be afraid of it. So we really need to kind of dive into this, and how fast and how deep, we just need to figure out on the way. So I would like to thank our speakers. You can also thank me, and we'll see you next time. Speakers are still here. You can torture them with questions. So come to our booth and you can actually try everything yourself. Thank you very much.